Because I think it's better if I share. Maybe, I don't know. I'm trying to go. Uh, how do I get? Because I cannot see my screen. Uh, Okay, let me. It. Just a minute. Yes, I can hear you. Let me. How can I start again? I mean, I don't see even Zoom anymore. Just. I know. Here we go. Okay, let me try. How is that? It's I mean, I see it. Can you see it? Okay, thank you. This is a talk on an absorbing ideal of commutative rings. And let me start by give you the definition that started in 2007, where if you take R to be a commutative ring, and then uh, uh, an ideal I, we call it two absorbing, as you see, if whenever you have three elements A, B, C in R and A, B, C in I, then A, B in I or A, C in I or B, C in I. So one way to think of two absorbing ideal, like generalization of a prime ideal, because the prime ideal means whenever you have a product of two elements in the ideal, then one of the elements should stay in the ideal. So another name for a prime ideal, if you want to use the concept of absorbing, 10, my colleague and friend Anderson and myself, we generalize this concept for any positive integer n. And here is the definition. Is everything still working? All right, thank you. Uh, so, like if you take a positive integer n, then an ideal is called n absorbing ideal if whenever you have n plus 1 element in R and the product of these n plus 1 element in I, then we want n of these AIs to stay in I. So like if you want to talk about three absorbing, what that mean, whenever you have a product of four elements in I, then a product of three elements of these four should stay in I. Okay, well, this concept uh, in 2013, Darani and Buzilski, I'm sorry about the pronunciation, um, they generalized this concept to semigroup in this article here. There are many work by ma these mathematicians, the number two, they generalize the concept to modulo and submodulo. And then there are other. who work on this. I will mention number four. In fact, this concept of two absorbing ideal, uh, they generalize it to non-commutative ring. It was generalized by the name of these two mathematicians in 2019. Okay, there are other articles that are related, but I will not have time to talk about, and you can see here, like this here is very similar to an absorbing ideal. There is another concept that's weakly to absorbing ideal that we will not have time to talk about. In fact, myself and I think I call him Onsal and Ij, my co-author from Marmara University in Turkey, number four and number five. We generalize this concept to primary ideals. And here is, yeah, I will mention number two, but we don't have time to talk about number two. These study rings, they characterize all rings where every two absorbing ideal is a prime. Because definitely, by definition, a prime ideal will always be two absorbing. But is two absorbing need to be prime? Not necessary. In fact, there are many examples where this is not true. So in number two, they characterize all rings where two absorbing and a prime the same. So every two absorbing is a prime. Okay, I will mention, there's no proof here. Some of the known result about uh, two absorbing ideal. Uh, this is a natural question, like if I is two absorbing ideal, will IX stay two absorbing ideal in the polynomial ring Rx? The answer is yes. And maybe you're going to see later on, what about if we remove 2? Like if I is n absorbing ideal, will Ix be n absorbing ideal? This is one of the open question till, to my best knowledge. This question is still open. They prove it for some classes of rings, but there is no proof in general, and there is no counterexample. So the conjecture is if I is in absorbing, then Ix will stay in absorbing for every n. This is still an open question. It's only known for some cases. Okay. The same thing, Malik and they prove similar result, but for the series R double bracket X, okay? Power series, they call it, formal power series. So if I is too absorbing, and there is restriction here on R need to be Noetherian, then this ideal stay too absorbing in here. Okay, we need to know some definition. What do we mean with SFT ideal? SFT ideal, we call it SFT ideal if there exists a number, n, and a finitely generated ideal L lives inside I, such that x to the n is in L for every x in I. Uh, of course, if every ideal is SFT ideal, then the ring, we call it SFT ring. So SFT ring mean every ideal is SFT ideal. Okay. Another definition, if you still familiar with the uh, Kroll dimension of a ring. Kroll dimension of a ring rely on the chain of prime ideal. The Kroll dimension, like you start with a maximal ideal, and then you build chain of prime ideals descending from M, like like Q1, Q2, Q3. Where is Q1 inside Q2, inside Q3, inside Q4, till you reach the maximal ideal. And you do that for every maximal ideal in the ring. You build a chain. The longest chain, this is what we mean with the dimension of the ring. The dimension of the ring is the longest chain of prime ideals that descending from a maximal ideal. So for each maximal ideal, you go and you build chain of prime ideal for each maximal ideal. And then the longest one, that will be the dimension. In this paper in 2016, they define n Kroll dimension, because remember that Kroll dimension related to the prime ideal, where n Kroll dimension uh, uh, will be related to the n absorbing ideal. So what they do, you go to definitely M is you start with a maximal ideal. So this is definitely two absorbing ideal. Then you start building chain of two absorbing ideal for each maximal ideal. So the longest chain, this is what they call it, the n Kroll dimension of the ring. This is what's written here. I just summarize it. Okay. Uh, what did they do in this work? Here is it. If you take R, of course, commutative ring, for each positive integer n, there is an n absorbing ideal of R, which is minimum among all n absorbing ideal of R. That's a nice result. And if you have a proper ideal of R, then for each positive integer n, there is an n absorbing that lie above I, which is minimum, which is very similar to, like, the concept of a prime ideal. Like if you choose an ideal I, then you look at the minimal prime ideal that over I. So that result is still true for n absorbing ideal. If you start with an ideal I, then you can build a minimal to n absorbing ideals that contain the ideal I. And this is, if R is Artinian, Artinian mean, the every descending chain of ideals terminate. Descending, not ascending. Ascending is for Noetherian. Artinian, whenever you do descending chain of ideal, then this chain should terminate at some point. It will not go forever. Like finite rings are always Artinian. If R is Artinian, then the n Kroll dimension of R is finite for every positive integer n. Remember, dim n, if I put n here 1, then this is nothing but the Kroll dimension, the classical Kroll dimension of the ring. Uh, but this is true for any n here. Okay. They prove another result. They gave a characterization of Dedekind domain in terms of the n Kroll dimension. You remember that what's Dedekind domain? Noetherian, and every ideal is invertible. Every ideal is invertible, meaning you can find another ideal, fractional ideal. When you multiply them, you come up with R. Anyway, R is, or another definition for Dedekind domain, every ideal can be written as a product of prime ideals. And this product will be, I think, unique. Uh, so Dedekind domain equivalent to uh, uh, the n Kroll dimension will be n. The 2 Kroll dimension of R will be 2. So it's enough to check 3. If the 2 Kroll dimension of R is 2, then definitely R will become Dedekind domain. Okay, here is, uh, let's look at this definition. Uh, Usually, like in case if you have a prime ideal, then the definition, then you give the definition in terms of element. But there is also another definition for a prime ideal. Whenever you have two ideals, and the product of these two ideals in I, then one of them has to be in I. In I, yes. The same thing here. We gave a definition for a strongly n-absorbing ideal. Let me stop. For n-absorbing ideal, we gave the definition in terms of element. Like you choose n plus 1 element, and the product of these n plus 1 element in the ideal I, then you want n of these element to stay in I. Here we added strongly n-absorbing. Strongly n-absorbing, the definition will be given in terms of ideal. Whenever you select n plus 1 ideals, and the product of these ideals in I, then n of these ideals, when you multiply them, these stay in I. That's the definition here. And here I will stop, and I can tell you, we conjecture that an absorbing ideal will always be strongly. Definitely, strongly in absorbing is always in absorbing. That's clear. But still, an open question. Still, here is a second open question. An absorbing ideal, will it imply strongly? Well, there are some mathematicians who work on some cases, and I will mention them. But in general, this question, to my best knowledge, is still open. Here is the conjecture. As I told you, if I is in absorbing, then I is strongly in absorbing. I prove this case in 2007 only when n equal 2. When n equal 2, 2 absorbing mean strongly 2 absorbing. In 2016, mathematician Goram Donadze, he added some condition that if R contains n minus 1 distinct invertible element, such that when you subtract Vi minus Vk stay invertible, then this conjecture is true, n absorbing strongly. But look, there is a condition here. You need to have a ring that contains that many invertible, and when you do the Vi minus Vk, these stay invertible. Sorry. Okay. Um, Let me remind you with the definition of U-ring. U-ring means uh, if you have an ideal that contained in a finite union of proper ideals, then I must contain in at least one of these ideals. So if you have I is a subset or equal to I1 union I2 union I3 union IN, then this ideal I should contain in at least one of these ideals. Uh, 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 Examples of U-ring are Proofer domain. Proofer domain meaning every finitely generated ideal is invertible. Or another definition, whenever you localize R at a maximal ideal, you get a valuation domain. So a Proofer domain is always U domain. Okay, this is a nice result in 2017 by Siham and Sana. I think they are from Tunisia. They prove that if R is U ring, if the ring is U ring, then conjecture 1 hold. So here is a nice uh, outcome of for conjecture 1. Conjecture 1 true for U domain or U ring. Sorry, U ring, in fact, your ring does not need to be domain. They prove it for any commutative ring R, that if the ring is U ring, then in absorbing means uh, strongly in absorbing. Here is another conjecture. Uh, as I told you at the beginning, this still open for n or bigger or equal 3. If I is in absorbing, will Ix be in absorbing in the polynomial ring? For n bigger or equal 3, still open. Like in 2010, we proved this conjecture for n equal 2. Goram Donadze, he gave if conjecture 2 is the true only for polynomial ring over z, the integer, then conjecture 1 will be true. So he relate conjecture 2 to conjecture 1. In 2017, Laraji, he proved that if conjecture 2, this conjecture, in absorbing implies Ix is in absorbing of the polynomial ring, then conjecture 1 is true. So if you prove conjecture 2, then by this result, you get 143. Okay? Um, the same number 4, they add one condition. These author, if your ring is U ring, and at the same time, what do you call it? Gaussian or Gaussian ring. Gaussian ring has to do with the content of polynomial. But anyway, uh, like the content, a content of the product is the same. But this is definition. We will not get to it. But uh, the conjecture is true for this type of ring. Okay, so this is what I know so far about. Maybe there are other things. Okay, here is conjecture 3, and I can tell you quickly, conjecture 3 is solved in a positive way. And in fact, there are two papers on conjecture number 3, like independent proof. In fact, very different proof. The history of conjecture 3, that if I is in absorbing, then if you take the radical of I to the power n, then you stay in I. Okay? That was our conjecture in 2010. Well, I proved that in 2007 for n equal 2. Laraji proved it for n equal 3. Siham and Sana, they prove it for 3, 4, and 5. And then here they were like, I think that was part of their PhD thesis, University of California. They prove conjecture 3 for every n bigger or equal 3. A recent student, uh, I believe that was part of their PhD thesis. And then in 2018, in an independent proof, again, Goram Donadze, he gave a proof of conjecture number 3. So conjecture number 3 is now true. Only left conjecture 1 and 2. And remember that conjecture 1 and conjecture 2 are true for some cases, but we don't have example to show that in some cases is not true, and nobody prove it in general. Our feeling that conjecture 1 and 2 are correct for every n. But, feeling will not work in mathematics. We need a proof. Okay. Uh, Definition of arithmetic ring, it means whenever you localize R at a prime ideal, you localize R at a prime ideal, then R will be totally ordered, the ideals will be totally ordered by inclusion. In another way, you can say R localized at prime ideal is a valuation or a chain ring. A chain ring, in a way. He proved that conjecture number 2 is valid. What is conjecture 2? That if I is in absorbing, then Ix stay in absorbing. All right? So for this class of rings, he proved it's correct. Okay, combining our result with the two, the after, the proof conjecture number 3, we end up with this. If R is arithmetic ring, For example, you can think of R as Bruford domain. If I is in absorbing ideal, then the following statements are true. All three conjectures are true when I is in absorbing ideal. It will be strongly, the IX will be in absorbing, and definitely 3 is correct uh, by Chow and Walker and Donazzi. Okay? Uh, I don't think I have time to talk about that. Maybe I maybe should. Uh, yeah, I'd like to talk about. Uh, can you hear me? I okay. Here is something I'd like to talk about. Yeah. Yes. Here is a recent paper in 2018. Remember that uh, definition of Dedekind domain mean every ideal is a product of a prime. So here we have this paper. It appeared in Communication Algebra. They want to write every ideal as a product of two absorbing ideal. Because all of us know two absorbing ideals, generalization of a prime ideals. Okay, and Dedekind domain mean every ideal is a product of every ideal is a product of a prime ideal. So they define a ring and they call it TAF ring if every ideal is a product of two absorbing ideal. And they come up with very nice result. If I is a proper ideal, then the minimum, how many minimum prime ideal over I has to be finite. And of course, if your ring R is TAF ring, then when you do the quotient, you still get TAF ring. If you multiply uh, two two rings A and B are TAF ring if and only if the product is TAF ring. Again, TAF mean every ideal is a product of two absorbing ideals. Okay. I think I want to. He gave an example here of you can read. Uh, I want to end here. Yeah. A complete characterization, if you look at any TAF ring is a finite direct product of one-dimensional domain and zero-dimensional local rings have nilpotent maximal ideal. In particular, if you have a TAF ring of dimension 1 having unique height 0 prime, then this ring is a domain. Okay, for a ring R, the following are equivalent. The polynomial ring is TAF ring. R is von Neumann. R is a finite dot product of fields. That's a very beautiful result. So if the polynomial ring 2AF, then I know what is R. R is von Neumann. And that mean, in fact, look at number 3. R just a finite direct product of fields. Wow, that's beautiful. In fact, what surprised me, the people who work on this paper, I know one of them, my colleague from Romania, and when I was in a graduate student, uh, because I study something called pseudo valuation domain, and they gave the definition of a proofer domain in terms of like when you localize every domain at a prime ideal, you get a valuation domain. So my question was, what kind of domain do we have whenever we localize um, D at some maximal ideal and we come up with pseudo valuation domain? What kind of domains are they? That was my question when I was a student. And look at, I mean, I don't know, are we mathematician connected by spirit? I mean, this question was in my head for many days, for many years. It turns out that D is TFAF domain if and only look at A and C. So the answer for my question is A, has to do with writing an ideal as a product of two absorbing ideal. And I like this result too much, A and C, that D is TF domain if D localized at M is B pseudo valuation domain. Okay, here's the last result, has to do with if you take the integers, remove 0, 1, and assume D is congruent to 1 mod 4, then Z, this extension, is a TAFD domain if and only if D is congruent to 5 mod 8. So here is like an example, has to do with numbers, and they are TAF domain. And I think I'm done, and I thank you. And I thank you, Jamil, for inviting me and for organizing a wonderful conference.